Hello, Calculus 2 students. This right here is the second part of 11.2, namely Introduction to Infinite Series. And this is definitely not easy. In fact, Infinite Series has the bad name of being the hardest part of Cal 2, but don't worry because I'm here for you guys. In this video, we'll be going over 4 examples, and this right here will be setting the fundamentals for the other sections, so be sure you guys take good notes on all this. And we will be building on the material. So let's look at the first one. We have 16, 8, 4, 2, and so on, so on, so on. This right here, we did it already, right? This is a geometric sequence. And we can, of course, write down a formula for that. An is equal to the first term, which is 16, times the common ratio is 1/2, and then raised to the n minus 1 power. That's it. And I'm not going to simplify it. Let me just leave it as how it is. Then, in the previous video, we also talked about the n's partial sum, and the notation is Sn. And what this means is that you start with the first term, which is 16, and you continue adding, right? Just keep adding the numbers here. And then you stop at the an term. So I will just put down an right here. So that's the idea. Well, this right here is geometric. So in fact, we have a very nice formula to add this up. And that formula is the following. We start with the first term, which is 16, and we multiply by the fraction 1 minus r, which is 1/2, and then raised to the nth power, and then we divide it by 1 minus r again, like this. Very nice, but unfortunately, it only works for the geometric series. And now, let me actually simplify this a little bit. And to do so, let me just multiply the bottom and the top by 2 right here. Because you see, inside here, 1 minus 1/2 is 1/2, times 2 is just 1, so it doesn't matter. On the top, because you see this and that on the outside, right? 16 times 2 is 32, and then you multiply by 1, we get 32. And then this is a minus, 1 to the n is always 1, and then we have 2 times 16 times 1, which is 32, over 2 to the nth power. So let me just keep it like that. And now we have the formula for the n's partial sum, and that's very nice. Now, let's look at the typical questions that the calculus class will be doing with this and that. The first one is, look at the sequence an, and we ask, does an converge? Well, in this case, all we have to do is just take the limit as n goes to infinity of the an. And now let me put it down right here. On the top, we have 1 to the n minus 1, which is just always 1. And then times 16, so we have 16 on the top. Over the bottom is 2 to that power, so let's write down 2 to the n minus 1 power. Then we see that right here, I can just put infinity to here, and 2 to the infinity minus 1 is going to be infinity. 16 over infinity, that will be 0. And after this, we can say an does converge, and it converges to 0. And we are done. Very nice. Now, again, we all note this right here, it's the keyword converge. And we can actually do the same with Sn as well. Because remember, if you look at Sn, the n's partial sum, you can break it down as S1, S2, S3, and so on, so on, so on. In another word, Sn is technically a sequence as well. However, Sn is just the series or the sum from the sequence originally an, right? So that's the difference and also the similarity. Let me write this down first. Does Sn converge? And if this is the question, all we have to do is to take the limit as n goes to infinity, and then just put down this formula and compute it. That's all. However, I do have to tell you guys that you actually don't see the question being asked this way often. Instead, the question will be asking you like this. We will say, does the sum or the series, this notation, you can either call it the sum or the series, or you can also say the sigma if you would like. But anyway, let's go from 1 to infinity of an. Because remember, this right here, it's pretty much you just add up a bunch of the things just like this. But this time, you have the infinity on the top already. This is the question that we will be seeing, but they are equivalent, right? They are equivalent. So just keep in mind with this notation really, really well. But anyway, all in all, we just have to take the limit as n goes to infinity of the Sn formula, which is this, and I just have to put that down. 32 minus 32 over 2 to the n. Well, when we put infinity to here, 32 over 2 to the infinity, which is infinity on the bottom, that will give us 0. 32 minus 0 will be 32. Done. And after this, we can say, yes, it does converge. It converges to 32. You can say Sn converges. Or, again, this is the form that we'll be seeing more often. So we'll be using this. We are going to answer this as the series as n goes from 1 to infinity of an. This right here does converge and converges to 32. And again, this is the question. That's how the question will be asking you instead of this. But again, they are equivalent. In the end though, I'll just write this down for you guys. Right? So now, let's think about why exactly this is happening right here. Instead of just, hey, the numbers is this, these are the computations, all that stuff. Have a look. Let's explain what this and that are talking about. First, let's go back to an converges to 0. What this means is that if you go back to the original sequence, 16, 8, 4, 2, 1, 1/2, and so on, so on, so on, right? You get the an. What's next? Well, you can just keep on going forever, but eventually, an is approaching 0 because that's what the limit is. So, if you take n to be infinity, in fact here, if you keep on going, in the end, you are pretty much going to get a bunch of zeros at the end, and then keep adding. You can see that, well, not adding, sorry, just keep writing down the zeros. Because you can see that you get 1, 1/2, 1/4, 1/8, 1/16, 1/32. The numbers are getting smaller and smaller, and they are approaching 0. That's what this is telling us, right? So now, let's look at what this is saying. The infinite sum is approaching 32. It converges to 32. This right here, again, same as that. We come back here. Let me write this down. This right here, the series as n goes from 1 to infinity of an. This is telling us to do this. 16 plus 8 plus 4 plus 8. Do we stop? We don't, because right here we have infinity. So you just add up these numbers, but you just keep going on forever. And just put on dot, dot, dot. And now this becomes a calculus question because we are dealing with infinity. If you stop right here, that's just basic arithmetic. If you put on plus dot, 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 that's calculus. And then what this is saying is that if you keep adding these numbers up, in the end, you will end up with 32. So earlier, you see this right here is approaching 0. The an terms are approaching 0, but in the end, if you add up the numbers, the sum is 32. And now you might be wondering, how come we are adding infinitely many numbers and then we can actually end up with a finite result? Well, I will tell you, if you want to just have a short answer for this, the answer to that is trust the math. That's all. Trust all the limits, math that you guys have learned. But let me actually take some time to explain why that was possible and that was actually the case, right? So have a look here. I will actually ask you guys a question first. Have you guys ever have experienced that maybe when you guys were 5 years old, that you're eating like, a piece of cookie? Man, it was so good, that piece of cookie, right? But unfortunately, you only had one amazing piece of cookie. If you have that experience, let me know in the comment down below. But anyway, here's the deal. after you finish eating that piece of cookie, wouldn't you be sad because it's gone? And you might not have another chance to eat it again, right? So here, let me show you guys a strategy that if you ever encounter something really, really nice, like another piece of amazing cookie, you can do the following and that cookie will last you forever. Have a look. Let's say this is the cookie. Nobody said a cookie has to be a circle. This is a square-shaped cookie, right? Well, if today you finish everything, that's not a good idea. You might be sad because you might not see this again, right? So let me tell you, go ahead and break this into 2 pieces and please just eat half of it, right? Well, what shall we do with this? Of course, save it for tomorrow. When tomorrow comes, well, don't eat the whole thing, otherwise you'll be sad. No good. So, let me tell you, please break this down into 2 pieces again and just eat half of the half. And that means you should just be eating 1/4 of it. And please save this piece for the following day. And when the following day comes, what should we do? Yes, you break this down into 2 pieces again, and then please just eat this piece and save the other piece for the following day. And then, following day comes, again, just do this only, and so on, so on, so on. And now let me ask you guys, if you are willing to follow this plan, can this continue forever? The answer to that is yes, right? You can just keep on going forever, forever, forever. All right, now let's keep track, right? Originally, we had this piece of cookie, right? But for the first day, we have eaten 1/2 of it. Next day, it was 1/4. And then next, we have 1/8. And next, we have 1/16. And again, hopefully you guys all agree with me that this process can keep on going forever. So if you're willing to keep on going on this, you can just put on ... Have a look here. On the right hand side, we have infinite sum. On the left hand side, we had 1. And this is finite. And we know this had to be 1. Why? Because we started with 1 piece of cookie. And we just do this procedure infinitely many times. So, as you can see, it is definitely possible that you have an infinite sum that gives you a finite result. Keep that in mind. Well, this is perhaps the reason why that this is called a geometric series, because you can draw a picture to illustrate the situation. And now this is what you have to know really well. This is one of the first tests that you have to know. This is called the geometric test, of course, geometric test. And I will tell you guys the following. You can also call this the infinite geometric series, whatever you would like, right? Geometric test. Here's the deal. If today you are dealing with an infinite geometric series, and the formula is n goes from 1 to infinity, and then we have a1, and then times the common ratio r to the n minus 1 power like this. Well, let me tell you, this right here, in fact, we have a nice formula. We don't have to do this every single time. The formula is, this right here is equal to a1 divided by 1 minus r's power. Right, 1 minus r, just like that, no power. Yeah. a1 over 1 minus r. And it's actually better if you remember this in words. a1 is the first term, and the r is the common ratio, of course. Right? So earlier, if you encountered this right here, what you could have done is the following. Actually, let's do this example right here. Let me use this formula to show you how we can get 32. First term, as we can see, right here we have 16. So we just have to write this down. This is equal to 16, and then divided by 1 minus the common ratio, which is 1/2. And now, on the bottom, 1 minus 1/2 is 1/2. 16 divided by 1/2, we end up with 32. And we are done. Very cool, huh? Remember earlier we took the limits of this, but now we have a very nice formula. Well, you might be wondering how come this formula is true. It's actually based on the formula that we have seen from the partial sum. Notice here we had a 1/2 to the nth power. In order to deal with infinity, you take n to be infinity. If n is infinity, 1/2 to the infinity's power is 0. So you don't have that anymore. 16 times 1 over this, which is exactly that. However though, notice this turns out to be 0. It was because we have 1/2 inside. And in general, in order for us to use this formula here, you have to make sure the R value, the common ratio right here, the absolute value of R has to be less than 1 in order for you to end up with 0 right here for this part, just like the 1/2 here. Imagine if you had negative 1/2, that would still work. But if you have positive 3 right here, sorry, it wouldn't work anymore. Again, if you have that positive 3, that means the numbers are getting bigger and bigger. You actually do not have a finite sum anymore. Alright, keep this in mind. This is the infinite geometric test, right? We'll be using this a lot, and this is one of the easier tests that we will be seeing, right? So I will, take some time to appreciate this right now. Yeah. All right, so that's about it for the first one, and I would also like to say, you see that right here, this turns out to be a finite value 32. The connection between this and that is you can just take this and multiply by 32. 32 times 1/2 is 16. 32 times 1 over 4 is 8, and so on. Yeah. All right. Now, I'm going to leave that on the board because here is the next example that's rather different. So here we have 4 over 9, 5 over 11, 6 over 13, 7 over 15, and so on, so on, so on. The next one should be what? 8 over 17. Have we seen this already? Yes. So let's go ahead and just do this real quick. Let's have the an here. Well, let's write down the formula for an. An is equal to the formula on the top. You see, you just keep adding 1. So we have 1 times n. And when n is 1, put it here. 1 times 1 is 1. Plus what will be 4? Plus 3, right? So plus 3 right here. Divided by, on the bottom, we just keep adding 2. So the 2 is the coefficient of the n. Put 1 in here. 1 times 2 is 2. Plus what will be 9? 7. And this is how you can come with the formula in no time. Yeah. All right. Here's Sn. Here's An. I will give you a challenge if you like. How can you find out Sn? Well, to do this, unfortunately, this right here is not a geometric sequence. It's not arithmetic. We do not have a nice way to add it up. In fact, it's pretty hard. Well, I don't even know if it's possible. So I'm going to skip the Sn part right here, right? This right here, in fact, I don't know, and in fact, we don't need. All right. Now, let's go back to the questions that we were studying earlier. First part is, does An converge? Well, for this, I just have to take the limit as n goes to infinity of the An formula, which is just n plus 3 over 2n plus 7. Well, do the limit the easy way, just ignore the 3 and the 7. N to the first over 2n to the first, n's reduced, so we just have 1/2. We are done. So right here, does An converge? We can say An converges to 1/2, and we are done. Very nice. Now, for the second part, of course, let's look at, again, the way that the question will ask you, which is, does Sn converge? But we write it as the series, or the sum, and goes from 1 to infinity, and you put the An right here. Does this converge or not, right? So now, again, what does this mean? Just like this right here. This was, you look back to the sequence and then just add them up infinitely many times. So what this means is that you look back to this, we are trying to see if we do 4 over 9 plus 5 over 11 plus 6 over 13 plus ... forever, do we end up with a nice value for this? What do you guys think? In fact, this might be harder because you are thinking we don't have a formula for Sn. So this is not doable at the moment. I don't know. Well, let me tell you, if we go back to what we talked about earlier, this right here is actually much easier than anything else. Alright, have a look. So again, let's talk about what does the 1/2 mean. The 1/2 means an is approaching 1/2, an is converging to 1/2. That means if you keep on going, in the end, these numbers are pretty much just like 1/2, right? They're just pretty much like 1/2. Let me just write this down. And then 1/2, 1/2, 1/2. And you can see we have 7 over 15. That's about 1/2 already. The next one is 8 over 17. That's about 1/2 already. This is approaching 1/2. An is converging to 1/2. Now, if you look back, does the series as n goes from 1 to infinity of an converge? Well, the first few terms we're just adding this. But eventually, we will be adding bunch of 1/2. We'll be adding bunch of 1/2 because that's pretty much what the end result will be. And imagine if you can make 50 cents, about 50 cents per day for infinite amount of time, how much money would you be making? Infinity. This right here, it's actually very easy. This right here will actually give us infinity, right? And because this right here is not finite, we'll just say this right here, unfortunately, we'll say the sum as n goes from 1 to infinity of an, this right here actually diverges. Well, now you might be wondering, how come this one diverges, but this one converges? Now, here's the deal. This right here converges because we had a chance. Because if you look at an converges to 0. That means right here, we are eventually adding 0. Bunch of 0, which they are not going to contribute too much to the finite sum. However, if you're adding bunch of things that's not 0, then this right here will make the whole thing infinity, like this, right? And in fact, we have a much easier way to reason this out. And let me write that down right here for you guys. But be sure you guys know the difference between this and that. This right here, we're just adding bunch of zeros. This right here, we're adding bunch of 1/2. This diverges. This right here converges. So here is the deal. Let me write this down for you guys. This is called the test for divergence. Test for divergence. And abbreviation is just TFD. That sounds kind of cool, huh? So now, here is what the statement says, right? Right here. Whenever you see that your an is converging to a finite number that's not 0, you can say the series of an diverges. That's pretty much it. I'll write this down. If the limit as n goes to infinity of an, in fact, as long as this right here does not give you 0, then we can draw a very nice conclusion that the sum as n goes from 1 to infinity of an, this right here, diverges. And again, this is another test that we will have to know. So earlier was a geometry test. This right here is a test for divergence, TFD. So right here, you didn't even have to write this down. It's just that it should help you to understand what was happening. Once you see that the limit as n goes to infinity of an is 1/2, you can just go right here to here and say the series as n goes from 1 to infinity of an diverges, and please be sure to give a reason. You have to say by test for divergence, right? And that's it. That's it. That's it. That's it. Now, here is the deal. You might be wondering, what if the limit as n goes to infinity of an does equal to 0? Does that promise you always end up a finite value like this? Well, unfortunately, that's not the truth. So here is a warning for you guys. If the limit as n goes to infinity of an, if this does equal to 0, then you know what I'm going to say. Yes, do more work. Because we cannot draw any conclusion about this at all. Earlier we saw this right here converges. Now, for the next example, I'm going to give you one for this. So, have a look right here. So, example 3, let's consider 1, 1/2, 1/3, 1/4, and so on, so on, so on. Of course, this is just 1 over n. So let's go ahead and write down an is just equal to 1 over n. Does an converge? Yes, it does. You can just take a limit, right? But let me actually just do what we did earlier. In fact, this right here for Sn, if you want to do 1 plus 1/2 plus 1/3 plus dot 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 up to 1 over n, again, we don't have a nice formula for it, so I'll just draw a sad face. We don't need to do that because we are focusing on the calculus type of questions, meaning infinities, right? So let me just indicate all this nicely for you guys. Does an converge, right? If this is the question, what we'll do is we take the limit as n goes to infinity of the formula 1 over n. Put infinity to here, 1 over infinity is of course 0. So I can say an does converge and converges to 0. And we are done. Very nice. Now, again, unfortunately, we do not have any information about Sn. We cannot just take the limit. So let's focus on this. Does the series as n goes from 1 to infinity of an? And by the way, do not mix up the notation. Do not put down Sn right here. Because this right here, it's the sum already. It has the S already. It's the S, right? It's the Greek version S. Anyway, does this converge or not? What do you guys think? You can do this by psychology, right? Because I told you I was going to do an example like this already, so yeah. However though, let's write down what this means first. The sum as n goes from 1 to infinity of an, we go back to the original. This means we do 1 plus 1/2 plus 1/3 plus 1 over 4 plus dot dot dot, right? What do we get right here? Well, you might be thinking that earlier here, this is 0, so eventually we're adding bunch of zeros like this. So this is really, really bizarre, really, really strange. But don't worry, I'm going to give you guys a proof by Wolfgang Alpha, alright? So now, this is what you can do, right? So you can just trust me on this because I want to Wolfgang Alpha and I did this for you guys already. So if you want to see the comments, I will have that in the comments for you guys. Anyway, if you do 1 plus 1 over 2 plus 1 over 3. If I stop, this is just fractions. You can just add them up. But anyway, plus dot dot dot, let's say plus up to 10, like this. Take a guess how big this number is. If you have a graphing calculator that does the summation, you can go ahead and try it along the way as well. But anyway, this right here, I will tell you it's approximately 2.92. 2.928, right? And then so on, so on, so on, of course. All right. So we add up the first 10 numbers, we get 2.9. Now, how about if I do 1 plus 1 half plus 1 third plus dot dot dot, but this time, I'm going to end up with 1 over 100. Right now I have 100 terms now. If I add them up, take a guess how big this number is. Well, this number is about 5.187. Dot dot dot. Alright, next one we can do from 1, 2, 3, and so on up to 1 over 1000. But that's, play big, of course. Let's do 1 plus 1 half plus 1 third plus dot 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 plus 1 over. How about 1 with 10 zeros? What's that? Billion, 10 billion, something like that, yeah? I'm just going to write it as 10 to the 10th power. Huh? And you see, 1 with 10 zeros. This right here, it's a lot. I'm not going to even try to do it by hand. On Wolfram Alpha, you will see this is approximately 23.603. Now, as you can see, when we are adding more and more terms, these numbers, they are still going up. Even though I'm adding like more terms, even though this right here, it went up by just a little bit, like 18. But this is still going up, right? And just for fun, to just kind of impress you guys, let me write this down here. If we have 1 plus 1 half plus 1 third plus dot 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 plus 1 over. Let me ask you guys, do you guys know what a Google is spelled it this way? Google means, well, let me give you guys an example first. The word 100 means 10 to the second power, 1 with 2 zeros, yeah? Google means 10 to the 100th power, meaning 1 with 100 zeros afterward, right? So, let me have 1 plus 1 half plus 1 third plus dot 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 plus 1 over 1 Google, namely 1 over 10 to the 100th power. This is humongous, right? But if you use Wolfram Alpha, let me tell you, this is approximately 230.835. Dot dot dot. Man, we have a lot of numbers right here already, and this number is still going up. So, as you can see, if we have n that goes to infinity, if this is getting bigger and bigger, you can see the output will also be bigger and bigger for the sum, right? So in fact, this right here, when you add it up, this is actually going to give you positive infinity. Because this right here is not finite, we can just say that this right here diverges, right? This right here diverges. And again, I just want to give you guys this method just to show you the numerical approach. But there's a homework question that you can actually prove this without using Wolfram Alpha. So be sure you guys do that one and watch my video if you need help with that, right? So hopefully with the numbers, you can see we will end up with infinity. Because technically, Google is nothing compared to infinity. You can have 10 to the Google power. I believe that's called the Googleplex. Yeah. Anyway, here's the deal though. Let me tell you guys something for fun. You don't have to know this part, right? Because now you might be wondering, is there a fast way to add up 1 plus 1 half plus 1 third plus up to 1 over n? Here's just some fun facts, right? Fun fact. If you have 1 plus 1 over 2 plus 1 over 3 plus dot 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 up to 1 over n. First, oh, this is not fun fact, you have to know this. This is called the Harmonic Series. I'll just write this down, okay? Harmonic Series. And later on, you guys can just quote that from harmonic series divergence. And you can also quote with the P series. But yeah, anyway, this is called the harmonic series. Let me write it down better. Harmonic series. I'm very sorry about the spelling. Anyway, you do have to know the name, but here's the fun fact for you guys. If you want to know how to find out the sum of 1 plus 1 half plus up to 1 over n, let me tell you, this is actually approximately equal to the natural log of n, but you have to add a special number, and that number is called the gamma. This right here is the Euler's constant gamma. Gamma is the Greek letter right here, and this is approximately 0.577, right? And this right here, in fact, is true when n is big, right? So I just tell you guys for large n. And if you have infinity for n, then this is actually technically to be true, because that's how the gamma is defined, to be the difference between this and also the natural log. But anyway, let me just write this down better, I'm sorry. For large n, this is approximately natural log of n plus the gamma constant. And this is equal if you have n is approaching infinity. Again, just some fun facts. So if you would like, you can go ahead and just do the natural log of 10 to the 100th power, and then you add 0.577, you will end up with this, right? Another way to prove this is divergent is that, because you know this is approximately equal to this, put n to power infinity. Ln infinity is infinity plus 0.577 is still infinity. Diverges, right? So anyway, be really sure when you have an is approaching 0, we have to do more work for the series, because this right here could be a divergent, right? Example number 3. Now, let's do the final example for this video, and this is another series that you have to know. So far we have talked about 3 of them. The first one is the geometric series. Next one is the test for divergence. And then the third one is the harmonic, right? Technically. All right, number 4. Here is the deal. Here I'm going to move my chair. Anyway, here is the one. Let's do 1 over 2, and then 1 over 6, and then 1 over 12, 1 over 20, and ... Oops, no, just put down ... And then, of course, we have the an here. So now, 2 questions. Does an converge? And does the sum of an converge? Well, let's come up with a formula for an. We actually have seen the 2, 6, 12, 20 already. This is just a 1 over that. To do this, pay attention to the 2 is the same as 1 times 2. The 6 is the same as 2 times 3. 12 is the same as 3 times 4. And then 4 times 5, etc., etc., right? So, as we can see, an is equal to, again, we have the 1 on the top. This time is over. N starts with 1, it matches with this, so it's just actually just n. And then times, this is 1 more than that, so we have n plus 1 right here. Just like this. So that's our formula for the an. Now, again, let's maybe try to find out what Sn is. And this time, we can actually find out what Sn is. I will do that for you guys. So, let me just put down for Sn. I want to find out a formula for that. I will actually do it like this for you guys. And I won't ask you guys to find out the Sn if it is extremely difficult or impossible. I will only ask you guys to find out the Sn when it's reasonable, just like the following, right? Sn, what we do is, we look at S1, which is just 1/2. And then we look at S2. And remember we did this in the previous video already. You just go ahead, write down a bunch of them and see a pattern. Anyway, S2 is 1/2 plus 1/6. And we cannot be lazy, we just have to add out the fractions. So let me just multiply by 3 and 3. On the top, I will get 4. And on the bottom, it looks like we'll still have the 6. And perhaps it's a good idea to reduce, so we have 2/3. Pretty good, huh? Then S3 is just 1/2 plus 1/6, and then we have 1/12. And yeah, that's what we have. The fast one is this right here is already 2/3, and we just add the 12, right? Multiply by 4, multiply by 4. That's 9 on top over 12. It's reducible by 3, so let's just do the fractions, 3/4. All right. Now, S4, let's do one more. S4 means we have to add up 1/2, 1/6, 1/12, 1/20. What do you guys think what this is? You can go ahead and add the fractions, but I will tell you this right here is equal to 4/5, haha. 4/5. Do we see the pattern already? Yes. Here we have 1, here we have 1, here we have 2, here we have 2, here we have 3, here we have 3. And please just add the fractions on your own to verify this. But when you have 4, this right here is also 4. What's the connection between the bottom and the top? And just one more. So if you want to figure out Sn, the top will just be n, and then divided by the bottom is 1 more than that, so I'll just put down n plus 1. So they are two very different formulas, and the way to do it is like this, right? So now we'll see if the usual thing, right? First question, does an converges or not? Well, take the limit as n goes to infinity, and then there we have 1 over n times n plus 1, like this. This is straightforward because you can just put the infinity here and here. We get 1 over infinity, and we end up with 0. So we can say an converges to 0. And with that, we are done, right? So this right here is it. An converges to 0, like this. All right, great. Now, next, does the series as n goes from 1 to infinity of an, does this converge? Earlier, we have seen 2 examples already that this right here diverges, right? But here we have a different example. And for now, let's see how we can do this. Well, one way to do it is that you find out the Sn formula, and which we did, and we take the limit of that. So here, we take the limit as n goes to infinity, and you write this down, which is just n over n plus 1. And does this converge? Yes, if you put infinity, right, you can work that out. You can just ignore the 1, which you actually just end up with 1. So based on this, we can say the sum as n goes from 1 to infinity of an, this right here, does converge, and it converges to 1. Be sure, there are 2 very different questions. And the truth is, we had to do more work because this right here is equal to 0. And we end up with a sum in this case. Earlier, example 3, an converges to 0, but the sum of an diverges, right? So this right here is pretty much the idea. But here's the bonus part. This is the usual strategy, but however, sometimes it's really hard to find out the Sn. And the truth is, sometimes it's really hard to find out what is this converging to. So sometimes we'll just be asking, does this converge or not? You just tell me if it converge or not. And you only have to tell me the answer, like the numerical answer, only when I ask you, like find the value for this, right? However, I want to show you guys a way that we can get the one right here without doing this for this particular question, right? So let's go ahead and do that. So this is like a bonus part. Here is the deal. I want to do this, and an we know is that already, so I'll just put this down for you guys. Here, I will just do the following. I'm just going to say, evaluate. This is a keyword that will tell you that go ahead and compute the answer for it. And I will just write down this right here, just be straightforward, 1 to infinity, and then I will give you guys the an formula already, which is 1 over n times n plus 1. I will say something like this. I will say if converges, right? So it's an indication that go ahead and give me the numerical answer for it. Now, here is the deal. Here's the an. It's 1 over n times n plus 1, yeah? You can do what we did earlier, find out the formula for the partial sum. But you can also do the following. Have a look. Here, just recall our usual integrations when we have to integrate 1 over x times x plus 1. What do we do? Partial fractions. We will also be doing partial fractions here. So here, let's go ahead and write this down. Here we have the sum as n goes from 1 to infinity. The first fraction, it will be some number over n. And then the next fraction will be something over n plus 1. And what's your favorite way to figure out these numbers? Yes, cover up, right? So to figure this out, we go back to the original, cover this up, and we have to make n equal to what? 0. And we put 0 in here. 1 over 0 plus 1 is 1. So here we have 1. And then we do the same thing. To figure this out, we go back to the original, we cover this up, but n has to be what? In order to have n plus 1 to be 0, n has to be negative 1. And we put negative 1 right here. 1 over negative 1 is this. Just negative 1. Now, you'll see that this and that, they're actually the same kind. And in fact, this is positive, that's negative. Here is the good hint, right? That's the hint that you should be doing the following. This is what we call a telescoping series, right? This is an example of a telescoping series. Let me just write this down. This is the telescoping series. And the reason that this is called the telescoping series is that the good old day, the telescope looks like this. And then you can collapse into just like the small one. Okay, here, let me show you. First, when n is equal to 1, you put it here, and then you are going to just write down the result. So have a look. Put 1 in here. The first term is 1 over 1. And then next we have minus, and then we will have the 1 right here. Put a 1 in here. 1 plus 1 is 2, so we have a 2 right here. So this is our first term. And then we continue. Next, we add, because the summation tells us to add the next term. N is 2, put it here. So we get 1 over 2. And then minus 1 over 2 plus 1, which is 3. And then we just continue. So we'll just be adding here. Next one will be 1 over n is equal to 3, because we're in the third parentheses. So we have 3 right here. And then minus 1 over 3 plus 1, which is 4. And then we'll just put on plus dot dot dot. However, do not just put on plus dot dot dot. What you should be doing is, you should also be putting down the nth term formula. Namely, just write this down. So plus 1 over n minus 1 over n plus 1. And you stop. You might be wondering now, here we have infinity, here we don't. Don't worry. We are from here to here. This is technically finite, yeah? But I will be taking the limit as n goes to infinity. So this is how you take care of this situation. And I'm very sorry about the little boards that I have right here. Let me write it down better for you guys, sorry. Didn't budget enough space for the first part. So I take the limit as n goes to infinity, right? So this was the equal sign here, and then the first term was 1 over 1. And then we have the minus 1/2 right here. All right, much better. And then we should have this parenthesis in black. That would be that. All right, much better. Whoa. All right, now, if you pay attention to the inside, you should see something interesting happening. Because here we have negative 1/2, but what do we have here? Positive 1/2. So, of course, we can cancel this out. Similarly, this is negative 1/3. Here we have positive 1/3, so we can cancel this out. Next, we have negative 1/4, but we will have a positive 1/4 next. We just didn't write it down. And so on, so on, so on, right? And the truth is, you will see that something right here can be cancelled out with this term, right? Have a look. In the beginning, we have just 1 now, and there's nothing else. At the end here, we have minus 1 over n plus 1. So I will put down this is equal to. In the front, we have the 1. In the end here, we have minus 1 over n plus 1, like this. And this is the quicker way to do it. I will demonstrate this in the homework questions as well. But if you look at n and n plus 1, they are off by 1. So in that case, in the front, you will just have 1 term remain. In the end here, you will have 1 term remain, right? So you have a total of 2 terms, like this. However, let's just finish this. We'll take the limit as n goes to infinity. And, of course, now, if you put infinity to here, it's 1 over infinity, which is 0. 1 minus 0, that will give you 1. So, this right here, we can say the sum as n goes from 1 to infinity of that 1 over n plus 1. Not only we know this converges, but we also know that this right here converges to 1. And in the end, we'll actually write this down as equal to 1. Right? And this right here is what we'll be doing a lot later on. However, it's not the case that we will get a finite value every single time. It's not the case that we can always end up with a nice number every single time, even though it converge. But in the next section, we'll be talking about different tests to see if an infinite series converges or not. That will be our main focus. All right, that's pretty much it. And again, let me know if you guys have any questions. By the way, if you notice, this is our Sn formula. It's equivalent to this. Anyway, as always, that's it, and I'll see you guys in the next video. Bye.